Hello, and welcome to the slideshow on atoms, isotopes, ions, and molecules. This corresponds with Chapter 2 in either the biology book or Biology by Boundless. By the end of this section, you should be able to define matter and elements, describe the interrelationship between protons, neutrons, and electrons, and compare the ways in which electrons can be donated or shared between atoms to create bonds, as well as explaining the ways in which naturally occurring elements combine to create different molecules. Everything is made up of atoms. An atom is a bit of matter that cannot be broken down further and still maintain its properties. So what you see on the right is a single atom of gold. An element, on the other hand, is a pure substance comprised of one particular type of atom throughout, and which you see on the lower right is gold bars. They are comprised of nothing but gold atoms, and that is an element. Atoms themselves are comprised of a nucleus on the interior, which has at least one positively charged proton and generally one or more neutral neutrons. They have no electrical charge. And orbiting around in one or more orbitals or shells are negatively charged electrons. The atom is held together by the attraction of the positively charged protons and the negatively charged electrons. Most of the mass, pretty much all of it, is comprised within the nucleus, for the protons and neutrons have approximately the same mass, and the mass of an electron is practically negligible. When we look at the information about different atoms, this is how each atom will look on a periodic table of the elements. Generally, you'll have the atomic number listed, and that's the number of protons. And of course, if the atom is neutral, if it has the same number of protons and neutrons, then that will also be the number of electrons. An ion will form when the number of electrons changes. As you can see by the atomic mass number, the atom itself is defined by the number of protons. The atomic mass is the average number of protons plus neutrons. The number of protons for a particular atom can never change, as the proton number defines each particular atom, but the number of neutrons can change, and that will lead to different isotopes. You can also see that generally the name of the atom is listed along with the atomic symbol. So the symbol for hydrogen is a single capital H. As we look at the periodic table, and in your OER textbook, this periodic table is listed on page 42, we can learn some things about each of the atoms. So how many protons does Li have? If we go up into group 1, and this is period 2, we see the Li here, and this is the element lithium. How many protons does it have? Well, that is the atomic number, so it has right up here in the top left-hand corner, it has 3 protons. And the number of neutrons we can get by looking at the atomic weight and taking, rounding that number, which is 6.94, would round to 7. So the atomic mass is 7. We subtract 7 minus 3 and we get 4. So generally, on average, lithium will have 4 neutrons. So 3 protons from the atomic number and 4 neutrons by subtracting the atomic number from the atomic mass. What is the atomic symbol for titanium? Well, I know that it's a little bit small, but if we go down and read through each of the atomic names, we will see down here titanium, and the symbol for that is Ti. How many electrons does titanium have? Well, we have to remember that the number of positively charged protons and negatively charged electrons will be the same in an uncharged atom. So if we look at the atomic number, 22, that is how many protons it would have. So that is also the number of electrons. So we see the atomic symbol is a capital T, lowercase I, very important that the second letter in any atomic symbol is lowercase, and it has 22 electrons to correspond with the 22 protons. And finally, if we look for how many more protons does P have than B, the number of protons is going to be the atomic number, which is again the number in the top left-hand corner. So for P, it is 15. For B, it is 5. We subtract these two to see how many more, and we get 10 more protons in P than B. And these atoms, if we look at the bottom for the name of the atom, we get P is phosphorus and B is boron. So 10 more protons in phosphorus than boron. Go ahead and look at page 42 and find the answers to each one of these questions. Pause the video now while you do that, and press play again once you've answered each of the questions. So hopefully now you've had a chance to answer each of the questions, and as we look, we can see each one of these answers coming sequentially. If you have any questions or missed any of these and are not sure why, feel free to either send me an email or send me a Sally message, and you can pause the video to take as long as you would like to check over each of these answers. So if we look at the entire periodic table now, there are an amazing amount of things that we can learn by looking at the periodic table. This was put together by a chemist and sort of Renaissance man. He did a whole bunch of things, Dmitri Mendeleev. And one thing that he did was place these atoms in order by the number of protons, so by their atomic number. Another thing that we're able to get out of this is by looking at the different groups, and you see that the groups are the columns, we can also learn a lot about the properties. Each one of the atoms within a group is going to behave in a very similar manner to each other. And as we look along each of the periods, which are the rows, we're going to find a stable pattern of generally increasing size, increasing mass, and some other chemical properties which are not going to be relevant within this class. But also, we can learn a lot about what each of these atoms would look like by looking at the periodic table. The number of groups, again, those are the columns, are going to indicate the number of electrons in the outside ring or shell or orbital, and these are the electrons that are going to be responsible for how that atom bonds. The periods, or again, the periods are the rows going across, they're going to indicate the number of electron orbitals. So we can gain a lot of information about how they're going to bond by creating what's called a Bohr diagram. Bohr was another chemist who figured a lot about how these electrons are going to relate to the bonding. And we can look at these just by seeing where each atom lies on the periodic table. So if we look at hydrogen, any atom in period 1 is going to have one orbital, one ring for its electrons, and we see that at the bottom there with hydrogen. Because hydrogen is in group 1, it's going to have one electron in that orbital, and so we can place it right there. If we look at a second one, say we look over at the other side of period 1 at helium, it's in period 1, so it's going to have one ring. There it is at the bottom. And because it is the second atom in this period, it's in group 18, which is the second group in this period, it's going to have 2 electrons. And there they are. And as we can see, since there are only 2 atoms there in that first period, it can only hold 2 electrons. The second shell, you can see if you count across Li, Be, B, C, and all the way over to Ne, there are 8 atoms, or 8 different elements in that period. That orbital, the second orbital, is able to hold 8 electrons, and same with the third. So as we look at lithium, Li, is in the second period, so it's now going to have 2 rings, 2 different orbitals for its electrons, and it is in the first group, so its outside orbital, orbital 2, is going to have 1 electron. The inside orbital, the first orbital, is full. And if we continue the same pattern and go over to the N, we see that nitrogen is in the second period, thus it will have 2 orbitals, and it is the 5th atom over. It is in group 15, or 5A, so it's going to have 5 electrons in its outermost orbital, and the inside orbital is going to be full. So we see the 1, 2, 3, 4, 5 different electrons in the outside orbital, which means that it is going to have all 5 of those either available to give, or it's going to be able to take 3 more so that it will be full. So pause the video and try to construct the Bohr model for carbon. Press play again once you're ready. So hopefully you've had a chance to construct the Bohr model for carbon, and as you can see here, it's in the second period, so it has 2 shells, 2 orbitals. The innermost orbital is full, it has 2 electrons, and the outside orbital has 4 since it is the 4th atom over and is in group 14. So these electrons, as I said, are going to be the same. The number of electrons in the outermost orbital is going to be the same within a group. For group 18, those are the ones all the way over on the right, their outermost shell of electrons is always full. That's going to give them the property of being inert. Helium, neon, argon don't tend to bond or react with other atoms. Thus, they're called noble gases, and that's what makes helium particularly good for, filling a child's balloon. You don't have to worry about it reacting with anything else and, say, exploding, like hydrogen, which is quite explosive, very reactive, because it has the need for one more electron in its outside orbital to be full, or it needs to give away that electron for essentially there to be no electrons, for the innermost one just to be full or have none. And what the other atoms, all of those not in group 18, are going to anthropomorphically want to do is they're going to want to bond. They're going to want their outermost orbital to be full, either by sharing electrons with another atom, giving the electrons away, or taking in their electrons. Now, of course, if they give or